Hey all, we've got a really maybe theoretical problem here on page 359, section 6.3. Assume that events A and B are non-empty independent events. Show that A and B must intersect, i.e. that the probability of A and B cannot equal the null set. By the way, note that this is not zero right here. This is actually called the null set. But what we're saying in effect is if it's the null set, the probability would be zero. So sort of similar. But anyway, how do we do this? We need to construct maybe a proof or some sort of like logical reasoned argument to demonstrate that if we assume that they're non-empty, A and B, okay, and that they're independent, they have to intersect, as in this condition has to hold that they can't equal zero. Well, what does it mean to say that it's non-empty? Non-empty means that they have something in them. So if you're talking about the probability of A, it can't just be zero. It can't just be nothing, because then we're not really talking about an event at all. It has to be something. The probability of A cannot equal zero, just like the probability of B cannot equal zero. Okay, good. Independent is also an important definition. We've been talking about that in class. Independent just means that if you have the probability of A and B, since they're independent, I don't have to think about the effect of B on A, and so I can multiply the events as if they were happening separately, and they are because they're independent. That means that the probability of A and B is just equal to the probability of A times the probability of B. So now that we know what we're talking about and we know that the conditions that we set, how do we show that they have to intersect? We can do it with something called a contradiction. And contradiction is a really common kind of method of proof in mathematics. It's just a way of showing that, okay, if we assume the opposite and we say that, for example, let's just suppose that the probability of A and B were in fact zero. Well, what's going to happen is we're going to get to something that won't make sense, and that will show that the opposite has to be true. Okay, so if we say that the probability of A and B equals zero, which is not exactly the same as the null set, but it's fine. If we say that this is in fact zero, then if it's independent, then we also know that the probability of A times the probability of B has to equal zero, just by the very definition of independence. They're the same thing. Now, if you have two things you're multiplying and it equals zero, then it also means logically that either the probability of A or the probability of B, or both, they have to equal zero. But notice what happened. We said that the probability of A or the probability of B equals zero, but this directly contradicts what we had just assumed in the beginning of the problem, which is that they can't be non-empty. So this can't work. Okay? This line of thinking can't work. We get to a contradiction. We get to something that doesn't make sense. Because of that, then this is true. That they must intersect. They can't be disjoint. All right, good. So we're on to that. Now let's go on to the next part. The next part says, why don't we use the results in part A to argue that if A and B are disjoint, they cannot be independent. Okay, fine. Very simple, easy to fix. We're going to basically work backwards here. Okay, so I just mentioned disjoint. What does the word disjoint mean? What is that as a mathematical idea? It just means that you have the probability of A and B equaling the null set or equaling zero. Okay, they're disjoint, they can't happen at the same time. A really simple way to think about something as disjoint is if I draw a card, I can't have the card be both a king and a queen. It's not possible. It has to be either a king or a queen. So the probability of drawing a card that is both a king and a queen would be the null set. There are no cards that do that. So this is disjoint. We're claiming that if this is disjoint, it cannot be independent. Well, let's again think about the contradiction. Okay, let's prove by contradiction that, assuming the opposite would have to be invalid. So suppose for a second that, since we're claiming that they're independent, it would imply that the probability of A and B would be equal to the probability of A times the probability of B. Okay? And now we're trying to show that, it cannot be independent, right? But we're saying that they are, right? If we're saying that they are independent, then this would have to hold true by the very definition of independence. But remember, we assumed this in the beginning. We assumed that this has to equal the null set. So on the left-hand side, the null set has to equal the probability of A and B. And I think very quickly you can see that we're going to run into a problem. Because if the null set equals the probability of A times the probability of B, then the probability of A or the probability of B, again, has to equal 0. But, again, this has to contradict, or it will contradict, what we had assumed about independence. So again, cannot work. This can't work. It doesn't make sense. And therefore, the opposite does make sense, that if they are disjoint, then they cannot be independent. So this is great practice on proofs. You might have seen some proofs maybe in calculus or maybe in a higher level math if you're taking anything like that. So definitely be getting in the mindset of just constructing logical arguments to really build a deeper theoretical understanding. All right, one final part. We need to find an example of two events that are neither disjoint nor independent. This will help us with our understanding of disjoint and independent, right? I can think of a pretty good example. Now, some of you may not like to hear this, but I gotta be honest here. I think your mom is actually a very, very important example here, okay? Now, your mom, I don't want to be mean, I don't want to talk too bad, but your mom is, well, let's just face it, she's obese. She's, in mathematical terms, fat, very fat, okay? Not pretty. But we can do something about this. We can actually fix this. And as you know, to fix a problem of being overweight, you do two things. You have to do diet and exercise. Diet and exercise are so important to lose weight. So what I would like to know is what would be the maybe combined probability that your mom, who is very fat, would somehow be able to get through a program that include diet and exercise? Well, I don't want to construct anything, I don't want to come up with any models, but let me just ask, are these events neither disjoint nor independent? Well, are they disjoint? In other words, could you not do one and the other at the same time? The answer is no. Because, in fact, you're supposed to do them at the same time. You can do both diet and exercise at the same time, no problem. Okay, so it is not disjoint. But is it independent? Okay, and so here's the confusion here, right? Many people assume that if an event or a pair of events are disjoint, then they have to be independent. But I would argue that they're not independent. My thinking, and there might be some debate here, but my thinking is that if you were to exercise or diet, or vice versa, then you would want to do the other at the same time. And it wouldn't make sense to just do one independently of the other. People who diet, in other words, tend to exercise more, and so I would argue that there's a conditionality to those probabilities, that doing one means you're more likely to do the other. So I would say that they're not independent either, even though they're not disjoint. Okay, and this can actually open up some discussion, because maybe, on a more serious note, think about how, in the real world, when they need to construct probability models, maybe of diet and exercise, maybe of other things like, certain earthquakes or certain natural disasters or certain, say, drugs and their ability to cure people or anything like that, they have to come up with assumptions about the model, right? And these assumptions may not be verifiable, but they have to make sense. I would say that, these assumptions about independence do make sense. We can follow them. They work, and they're intuitive. They are part of our experience. So this model fits. These events, I would say, are neither disjoint nor independent, but again, you may disagree, and it'd be very interesting, I think, to see in the comment section what people are thinking about this. So anyway, thanks a lot, guys. I hope this problem helped make sense.